Okay, welcome back. So I'm going to do a longer video. I'm going to read the book, but I'll start off with my AWS account closure confirmation. So this account is now closed. It is the third of the month, so I might still receive that another 50 cents charge this month, and there's nothing I can do about it. Um, so uh, it looks like you can look at past billing and my ad blocker. Oh no. So next month I'll get charged about $5. And you see what I mean? It's like I had no way of knowing that. So like I closed my account and I'm still going to get charged because I closed it on the third and I would have liked to have closed it the moment I got this charge, but it's too late. So they got about $5 out of me that I did not expect to spend. So imagine you are a large enterprise and they get $50,000 out of you that you did not expect to send. It could be the difference between your company uh, succeeding or not. So let's click info. So we've got an active service. So um, let's try to shut down the active service. So we saw that I was getting charged for DNS, but I don't see where. Oh, here we go for Route 53. So okay, I closed my account. So I think I might take another charge this month. And they might have charged me for closing my account. I don't know why it's forecasting that I would get charged. But again, now the other thing is, if this is just for the DNS service, now we're talking per month. This is a very high charge. You can buy a domain name for like $8 for the year. So if this is the price per month of just a domain name, this is a very very high charge. So yeah, I'm really unhappy with this. It's just been it took me by surprise, which I don't think is appropriate for a project with very tight constraints. Okay, so I don't have any active accounts anymore, so that's good. I do have. Oh, I have an invoice, but there's nothing. So charges by service, I think, is the big one. So I paid for taxes, and then I paid for this DNS hosted zone service, which is a very very high price if it is estimated to increase to about $4.50 next month. So anyway, moving on. We're beyond that part anyway. We're not learning about AWS anymore. We're doing machine learning, which I believe matters. AWS, cloud service. I I don't know. It's just I feel like trad networking is still very much a thing and very much a real possibility. And then I also feel like there's enough people trained in AWS that you can find someone like if it works, it works. It's not. But anyways, moving on. So cloud, yeah, cloud machine learning platform. So actually, this is kind of a timely subject because we're going to be learning about cloud in this next part. So one aspect of machine learning that is becoming ubiquitous is cloud-based machine learning platforms. Google offers GCP AI platform. So there we go. So here's the cloud-based. So I wish I could see that more clearly. I can kind of see it. Is there a way to... So here's the full screen. Is there a way to zoom in is what I want to know. No, there's not. Okay, so you can kind of see ML activity, so data, preparing the data, and then there's GCP services related to each machine learning activity in the cycle, and then there's a workbench and the repository. The GCP platform has many high-level automation components, from data preparation to data labeling. The AWS platform offers SageMaker, offers Amazon SageMaker. So here we can see the SageMaker architecture. We have our notebook, like a Jupyter notebook, I guess I'm assuming. Spot training instances, test data predictions loop there, and then another loop here between the trading data, AWS Lambda, and Amazon CloudWatch event C-time based. SageMaker also has many high-level components, including training on-spot instances and elastic protection endpoints. Machine learning maturity model. One of the big challenges right now is a realization that transformational change is needed in companies that want to perform machine learning. The machine learning maturity model diagram represents some challenges and opportunities. So here we go. So we've got 6 levels of challenges. The first level is framing, scope identification, and problem identification. The second level is continuous delivery of data. The third level is continuous delivery of cleaned data. The fourth level is continuous delivery of EDA. I'm not sure what that is. Probably another tier of data. Speculation is typically not a good thing. The next level, level 5, is continuous delivery of traditional ML and auto ML. And then level 6 is ML operational feedback loop. So this is the machine learning maturity model. So machine learning key terminology. I'll do an audio check. Looks good. Let's define some key machine learning terminology that will be helpful throughout the rest of the chapter. Machine learning, a way of building mathematical models based on sample or data training. Model, this is what the product is in a machine learning application. A simple example is a linear equation, for example, a straight line that predicts the relationship between an x and a y. Feature. A feature is a column in a spreadsheet that is used as a signal to create a machine learning model. A good example is points scored per game by an NBA team. Target. The target is the column in the spreadsheet you are trying to predict. A good example is how many games an NBA team wins in a season. Supervised machine learning. This is a type of machine learning that predicts future values based on known correct historical values. A good example would be predicting the amount of NBA wins in a season by using the feature points per game. Unsupervised machine learning. This is a type of machine learning that works with unlabeled data. Instead of predicting a future value, it finds hidden patterns by using tools such as clustering, which in turn could be used as labels. A good example would be to create clusters of NBA players that have similar points, rebounds, blocks, and assists. One cluster could be called tall top players. Another cluster could be called point guards who score a lot of points. Um, Deep learning. This is a type of machine learning that uses artificial neural networks that can be used for supervised or unsupervised machine learning. The most popular framework for deep learning is TensorFlow from Google. Scikit-learn. This is one of the most popular machine learning frameworks in Python. Pandas. This is one of the most popular libraries for doing data manipulation and analysis. It works well with scikit-learn and NumPy. NumPy. This is the predominant Python library for doing low-level scientific computing. It has support for a large multi-dimensional array and has a large collection of high-level mathematical functions. It is used extensively with scikit-learn, pandas, and TensorFlow. So level 1, which we saw in the chart back here, of the machine learning maturity model. So level 1 is framing, scope, identification, and problem definition. Let's look at the first layer. When implementing machine learning at a company, it is important to consider what problems need solving and how they can be framed. One of the key reasons for failure of machine learning projects is that organizations haven't first asked questions about what problems they need to solve. A good analogy to look at is building a mobile application for a restaurant chain in San Francisco. One naive approach would be to immediately start building a native iOS and a native Android app using 2 development teams. A typical mobile team could be 3 full-time developers for each application. So this means hiring 6 developers at around $200,000 each. 200,000. Wow. That's okay. So the run rate for the project is about 1.7 million a year now. Will the mobile app deliver greater than 1.2 million in revenue each year? If not, is there an easier alternative? Perhaps a mobile optimized web app that uses the existing web developers in the company is a better choice. What about partnering with a company that specializes in food delivery and outsourcing this task completely? What are the pros and cons to this approach? The same type of thought process can and should be applied to machine learning and data science initiatives. For example, does your company need to hire 6 PhD level machine learning researchers at, say, $500,000 a year? What is the alternative? A little bit of scoping and problem definition goes a long way with machine learning and can ensure a higher chance of success. And PhD level, what's his name? IIYER Open AI. Does he even have a? Yeah. So I'm not even convinced that just getting a PhD level person is a surefire. Oh no. Okay, so he does have a PhD. Okay, so yeah, that's a surefire. If you were a company like like OpenAI, then that's a definitely a good strategy. I was just wondering if some of these leaders didn't even have a PhD, but I think all of them probably do. I think even Sam Altman, who's just a management, probably has it. Oh, okay. Well, Sam Altman doesn't have a degree, but he's a manager, not technical. And then he is a very technically gifted person anyway. All right. So, yeah, that's probably a good strategy, but it's you know, maybe it's not the best strategy. So the first thing you need to do is frame, scope, and define your problems. If you're OpenAI, then you might need some PhDs. If you're not, then you need to uh, determine what you actually need. And then once you've determined that, you can move on to level 2, continuous delivery of data. One of the fundamentals of civilization is running water. Roman aqueducts carried water for miles to provide crowded cities with water as early as 312 BC. Running water enabled the infrastructure necessary for a large city to succeed. It is estimated by UNICEF that worldwide in 2018, women and girls spend an estimated 200 million hours daily collecting water. The opportunity cost is substantial. Less time to spend learning, taking care of children, working, or relaxing. A popular expression is that software is eating the world. A corollary to that is that all software companies, which is every company in the future, need to have a machine learning and AI strategy. Part of that strategy is to think more seriously about continuous delivery of data. Just like running water, running data saves you hours per day. One potential solution is the concept of a data lake, as shown in Figure 14-9. Okay, so we've got a data lake here with machine learning, on-premise, real-time, and analytics. And then there's S3 and AWS Glue for them all together. So you can't avoid AWS. As I showed in the beginning, you need to be careful with it. Make sure uh, you know what you're going to get charged and why. So that's part of the skill of using AWS is managing your charges. All right, so why do it? Why make a data lake? Because you get structured and unstructured data, you get analytics and machine learning, you can work on data without data movement, and you get low-cost storage. At first glance, a data lake might seem like a solution in search of a problem, or too simple to do anything useful. Let's look at some of the problems it solves, though. You can process the data without moving it. It is cheap to store the data. It is straightforward to create lifecycle policies to archive the data. It is straightforward to create lifecycle policies that secure and audit the data. The production systems are decoupled from data processing. It can have almost infinite and elastic storage and disk input and output. The alternative to this architecture is often an ad hoc mess equivalent to walking 4 hours to a well and back simply to get some water. Security is also a major factor in a data lake architecture, just as security is in the water supply. I want to say something about this. So The alternative to this infrastructure is an ad hoc mess of walking 4 hours to a well and back simply to get some water. Okay, well, if you need water, this is a good strategy to get water. So like, I feel like what happens to some people in some organizations is they're like, okay, there's a better way to do the thing we need to do, get water. So let's not do this thing and let's die of dehydration. Because there's a better way to fetch water than walking 4 hours a day to a well and coming back, we're just gonna stay here and die of thirst. It's like, okay, great. There's a better way to do everything. If you can have an AI infrastructure that works and it involves, suboptimal processes, hey, like maybe that needs to be part of your calculations too. Is like, if we're walking 4 hours to do a well and back simply to get some water, does that prevent us from dying of thirst? Because if it does, we should start doing that right away, even though it's not the best way to do it. And then later now that we haven't died of thirst, now we can think of a better way to do it. All right, so security is also a major factor in a data lake architecture, just as security is in the water supply. By centralizing the architecture of data storage and delivery, preventing and monitoring data breaches becomes more straightforward. Here are a few ideas that may be helpful in preventing future data breaches. Is your data encrypted at rest? If so, who has the keys? Are decryption events logged and audited? Is your data moving out of your network logged and audited? For example, when is it ever a good idea for your entire customer database to move outside of your network? Why isn't this monitored and audited? Do you have periodic data security audits? Why not? Assuming you don't. Are you storing personally identifiable information, PII? Why? Assuming you are. You have monitoring for critical production events. Are you monitoring data security events? Why not? Assuming you are not. Why would we ever let data flow outside of the internal network? What if we designed critical data to be a literal square peg that couldn't be transmitted outside? I don't think they mean literal. That couldn't be transmitted outside of the host network without something like a nuclear launch code, making it impossible to move data out of the environment. Does seem like a viable way to prevent these breaches. What if the external network itself could only transport round peg packets? Also, this could be a great lock-in feature for clouds, providing this type of secure data lake. Alright, so level 3 is continuous delivery of clean data. Hopefully you are sold on the idea behind continuous delivery of data and how important it is for the success of a company's plans for doing machine learning. One huge improvement to continuous delivery of data is continuous delivery of clean data. Why go through all the trouble of delivering data that is a mess? The recent problem of contaminated water in Flint, Michigan comes to mind. Around 2014, Flint changed its water source from Lake Huron and the Detroit River to the Flint River. Officials failed to apply corrosion inhibitors, which allowed lead from aging pipes leak into the water. And I think there's a typo here which allowed lead from aging pipes to leak into the water supply. It is also possible that the water change caused an outbreak of Legionnaire's disease that killed 12 people and sickened another 84. Jesus. What is Legionnaire's? Does not sound good. Okay, so it's a lung infection. It's a type of pneumonia. Does not sound good at all. Okay, so and it spreads through like air conditioning, through mist. It's not like a pandemic style disease. Okay, many people don't develop symptoms, but once you're over the age of 50 and are kind of on your way out, it's one of those things that will it's just sitting there waiting to get you. One of the earliest success stories of data science involves dirty water from 1849 through 1854. Jon Snow was able to. I think they're talking about the Jon Snow from Game of Thrones. Was able to use data visualization to identify clusters of cholera cases. This led to the discovery of the root cause of the outbreak. Sewage was being dumped directly into the drinking water supply. Dear, oh no! And cholera is terrible. Cholera is uh yeah, cholera. You just vomit and diarrhea all the water out of your body until you die from thirst. Cholera is really, really bad. It sounds like Legionnaires is not that bad. It's just kind of a comorbidity. It's not like an acute condition. But cholera is fatal if not treated right away. You die of dehydration because you puke and diarrhea out all the water in your body until you have none and die of dehydration. Cholera is bad. Don't get cholera. So do data science on your water supply, and detect sewage leaks. All right, so here's a map here. Let's see what the yeah. So oh cool. So awesome. No, this is really cool. So what he did was he created a data visualization of all of the cases. So I don't know how to read this map, but it looks like there's some black spots here. So maybe the cases are have to do with these black spots. So he isolated down based on where all these cases were occurring. Um, where is this leak in the water supply happening? Well, it's happening in the area where all the cases are happening. It's not happening over here or there or there. So now they can check all the plumbing in this area and fix the leak. That's cool. So consider the following observations. Why isn't data automatically processed to clean it? How can you visualize parts of your data pipeline that have sewage in them? How much time is your company spending on data cleaning tasks that are 100% automatable? So this is kind of a I think this is a good one for ChatGPT. So I'll leave the author information in there as well.
The quote referencing highlights an important issue in data science and engineering, the challenge of data cleaning and why it's not entirely automated. Let's break this down and visualize the concepts. Why data isn't automatically processed to clean the complexity and variety of data. Data comes in many forms and structures, from simple numerical values to complex, unstructured text and images. Each type of data can have its own dirty aspects like missing values, duplicates, or irrelevant information, which require specific cleaning strategies. Context-specific cleaning requirements. What constitutes clean data can vary widely depending on the application. For example, data that's clean for one use case, like trend analysis, might not be clean for another, like real-time decision-making. Automatic tools lack the domain knowledge to make these distinctions. Quality and interpretation issues. Clean data isn't just about removing what's obviously wrong or irrelevant. It's also about making sure the data correctly represents the real-world phenomena it's supposed to model. This often requires human judgment and contextual understanding that current AI and automation tools lack. Visualizing sewage in the data pipeline. Imagine a pipeline where data flows from its source to its finally used in analysis or applications. Along the way, it passes through several stages: collection, storage, processing, and analysis. Sewage, in this context, refers to parts of the pipeline where data quality issues arise: collection, incorrectly recorded data, missing values, or biased samples. Storage, duplicate records, outdated information, or data corruption. Processing, inadequate handling of missing values, incorrect data type conversions, or loss of information through oversimplification. Analysis, misinterpretation of data, incorrect assumptions about data distributions, or the use of inappropriate analysis methods for the data type. These areas can introduce errors or biases that affect the outcomes of data analysis or the performance of data-driven applications. Time spent on data cleaning tasks. Regarding the question of time spent on data cleaning tasks that are 100% automatable, it's important to note that while some aspects of data cleaning can be automated, like removing duplicates or correcting obvious outliers, many require a nuanced understanding of the data's context and intended use. Estimates vary, but data scientists often report spending 50% or more of their time on data preparation and cleaning. The percentage of this that is 100% automatable is hard to pin down and would depend on the specific tasks and the sophistication of available tools. However, advancements in AI and machine learning are continuously increasing the scope of what can be automated. Visualizing the concept. To visualize this concept, let's create an illustration of a data pipeline with areas marked as sewage to highlight where data quality issues typically occur. Let's create an image that depicts a data pipeline as a series of pipes and filters where data flows from left to right. Along the pipeline, we'll mark sections with sewage symbols like splashes of mud or trout icons at the collection, storage, processing, and analysis stages. Each section will have tools or workers attempting to clean it, with some areas cleaner than others, indicating the ongoing effort and the challenge of achieving completely clean data.
That was cool. I like how it drew a picture. Just kind of an artistic thing. It's not really like they misspelled collection. I don't feel like there's any real insight shown in the picture, but it's kind of cool that it was produced like that. All right, so now you can move up to level 4. Now that you've got data processing set up and your data is cleaned and you've isolated any problems and problem areas and fixed them, and you've got everything automated that you possibly can. Now you can move up to level 4, which is continuous delivery of exploratory data analysis. If your only view of data science is Kaggle projects, it may seem like the whole world of data, the whole point of data science is to generate the most accurate prediction possible. There is more to data science and machine learning than just making predictions. Data science is a multidisciplinary field, and there are a few ways to look at it. And here's the letter E. Looks like a typo. One perspective is to focus on causality. What are the underlying features that drive the model? Can you explain how the model is coming to the prediction it has generated? Several Python libraries help in this regard: ELI5, SHAP, and LIME. They all work to help explain what machine learning models are really doing. A prediction worldview cares less about how you got to the answer and more about whether the prediction is accurate. In a cloud-native big data world, this approach has merits. Certain machine learning problems do very well with large quantities of data, such as image recognition using deep learning. The more data and the more computational power you have, the better your prediction accuracy will be. Is what you created in production? Why not? If you are building machine learning models and they don't get used, then why are you building machine learning models? What don't you know? What can you learn by looking at data? Often, data science is more interested in the process than the outcome. If you are only looking for a prediction, then you may miss out on a completely different angle to the data. Alright, so now that you're no longer missing out on the angles, you can move on to level 5, which is continuous delivery of traditional machine learning and auto machine learning. Fighting automation is as old as human history. The Luddite movement was a secret organization of English textile workers who destroyed textile machinery as a form of protest from 1811 to 1816. Ultimately, protesters were shot, Well, there's a technology you can't ignore: a gun. The rebellion was put down with legal and military might, and the path of progress kept going. If you look at the history of humanity, tools that should laugh at these people with slaughter like that, but I just think it's yeah, you hear the word Luddite used a lot, so it's kind of interesting that there's real history behind that. If you look at the history of humanity, tools that automate tasks that humans once did are constantly being developed. In technological unemployment, lower skilled workers are displaced and higher skilled workers get an increased salary. A case in point is the systems administrator versus the DevOps professional. Yes, some systems administrators lose their jobs. For example, workers focused on tasks such as changing hard drives out of data centers, but new, higher paying jobs such as cloud architects appeared. All right. It isn't unusual to see job postings for machine learning and data science that command an annual salary of between $300,000 and $1 million. Additionally, these jobs often include many components that are essentially business rules, tweaking hyperparameters, removing null values, and distributing jobs to a cluster. The automator's law, something I came up with, says if you talk about something being automated, it will eventually be automated. And that's, this idea that you don't know what you don't know. If you can't talk about it, you don't even realize what it is clear enough to have it automated. So yeah, if you can discuss something being automated, it will eventually be automated. That's a good rule. There is a lot of talk about auto ML, so it is inevitable that large parts of machine learning will be automated. This will mean that just like other automation examples, the nature of jobs will change. Some jobs will become even more skilled. Imagine a person who can train thousands of machine learning models a day, and some jobs will become automated because a machine can do them much better. Jobs that involve tweaking values in a JSON data structure, for example, tuning hyperparameters. All right, I'm going to get to here and then I'm going to stop there. Level 6, final level. Machine learning operational feedback loop. Why develop a mobile application? Presumably to have users on a mobile device use your application. What about machine learning? The point of machine learning, especially in comparison to data science or statistics, is to create a model to predict something. If the model isn't in production, then what is it doing? Additionally, pushing the model to production is an opportunity to learn more. Does the model predict accurately when put into an environment where it gets new data? Does the model have the impact expected on the users? For example, increasing purchases or staying on the site longer? These valuable insights can only be obtained when the model is actually deployed into a production environment. Another important concern is scalability and repeatability. A truly technologically mature organization can deploy software, including machine learning models, on demand. The best practices of DevOps for machine learning models are required here as well: continuous deployment, microservices, monitoring, and instrumentation. One easy way to inject more of this technological maturity into your organization is to apply the same logic as you do to choosing cloud computing over a physical data center. Rent the expertise of others while taking advantage of the economies of scale. Alright, so let's show the notebook and delete the older One. Yes. Okay, great. I can make flashcards. That's good. Yep, so here's the new location. So that's going to be it. I don't have the capacity to continue. And then we've got a lot of practical hands-on that I think will be good to include in its own video. Oh, and I do have an old bookmark here that I'll get rid of. Alright, so that's it for this video. See you in the next one.